Okay, so it's an equivalence relation if it satisfies 3 extra properties. So those properties are reflexivity. Let's color code this a little bit. So reflexive, and that would be x comma x is in R for all x in A. That could be written as XRX, like using this notation up here. Then there's a symmetric, which says if XY is in R, then YX is in R. So if X R Y, then Y R X. And then finally, there's this one called transitive, which says if XY is in R and YZ is in R, then XZ is in R. Yeah, and I think last time we saw that this transitivity in a graph meant that if we have any path from one vertex to another, then we must have a direct path, right? So we looked at that kind of picture last time. Now, in some of the stuff that you guys did to prepare, you saw that equivalence relations gave rise to something called an equivalence class, equivalence classes, and also a partition of the set. So we'll talk about that in just a second, but maybe right now, let's look at some examples of equivalence relations. So maybe I'll do an example and then we'll sort of see if there are any questions about it. And then we'll have you guys do one of the problems and then we'll do it as well. Okay, so let's maybe look at this relation. So let's define R. So that's a relation on Z cross Z by X, R, Y, if X squared plus Y squared is even. Okay. So let's maybe look at some examples. So for example, 2 is related to 2 because 2 squared plus 2 squared is equal to, well, that's 4 plus 4, right? It's equal to 8 is even, right? And then here we're just exploring, right? So maybe this shouldn't be example so much as explore. You know, I think it's always a good strategy to like play around with the setup to get some sort of intuition for what's going on before we jump into the looking at all of the properties abstractly. Okay, let's maybe look at answer the question, is 1 related to 3? I think 1 is related to 3 because 1 squared plus 3 squared is equal to 10. And that's even, right? So 1 squared, sorry, 1 is related to 3. Now let's look at this. Let's say, is 1 related to 2? So let's think about this as a question. I'll put a cross through it if it's not, and you think it's not? Right, and it's not because
1 squared plus 2 squared
is odd. And we know that odd means not even, right?
Yeah.
Yeah. Okay, so it looks like all even are related to all other even, and all odd are related to all other odd, but all even are not related to all odd, right? It looks like that might be the case. And that's actually what we'll end up showing in the second part of the problem, which says prove or find the equivalence classes. But before we do that, let's show that it is an equivalence relation. So maybe we'll make this a proposition. R is an equivalence relation. So let's check the three properties. We have to check reflexivity, symmetry, and transitivity. So let's check reflexivity first. So let's suppose X is an integer. You know, maybe you want to use like n or something, because that's more typically an integer, right? So let's say n is an integer, and then notice that n squared plus n squared equals 2n squared, which is even, right? We can all agree that that is even, but the fact that n squared plus n squared is even means that n is related to n, right? So that means it's reflexive, right? Because what have we done? We've taken an arbitrary element from the set. That element is n. So we've got an arbitrary element from the set, and we've shown that that element is related to itself. Okay, so now let's do symmetric. So symmetric. So we'll suppose that M and N are in Z such that M is related to N, right? And then what we want to end up with is that N is related to M. So let's see how we can do that. So notice that that means that M squared plus N squared is even. That's by the definition of R, right? But we know that addition is commutative, right? That means that n squared plus m squared is even. Because it's the same. It's the same even number, right? But that means that n is related to m, which is what we want, right? So what did we do? We started with m is related to n. We ended with n is related to m, but that's exactly what we needed for symmetry, right? Okay, let's do transitivity. Okay, so what should we use as our third letter for an integer? L. Yeah. So let's suppose L, M, and N are integers such that L is related to M and L is related to N. No, sorry. M is related to N. Okay, so let's see. That means that L squared plus M squared is even, right? And M squared plus N squared is even. But what do we want to get to? We want to get to N, L is related to N, right? Well, we can do that by adding these two together. Notice if we add those two together, we have L squared plus 2M squared plus N squared is even, right? But we know this guy is already even because it's a multiple of 2. So that thing is already even. But that tells us that everything else must be even, right? So that ends us off with L squared plus N squared is even, which tells us that L is related to N. Okay, but that's transitivity, right? We started with this and this, and we ended with this. Okay, let's do the equivalence classes real quick, and then we'll take them. Okay, so equivalence classes. So like we had pointed out, it looked like all even numbers were equivalent and all odd numbers were equivalent, right? So we can actually write the equivalence classes maybe like this. Write it maybe like this. We'll take Z and we'll, so we've got even numbers. We'll write that as 2Z, and then odd numbers, we'll write that as 2Z plus 1. So those are the only two equivalence classes. The two equivalence classes. So how do we show that? Well, all we have to do is take two things from here and show that they're equivalent. So let's suppose that A and B are in 2Z, but that means that A equals 2 times M and B equals 2 times N for M and N in Z, right? That's the definition of being in 2Z. And then we've got A squared plus B squared equals 4M squared plus N squared, just by the fact that we have even numbers. Which is even, but the fact that that's even means that A is related to B. So that means everything that's even is related to everything else that's even. Now let's suppose that A, B is in 2Z plus 1. So, and now we want to show that these are related. So this tells us that A is equal to 2M plus 1 and B is equal to 2N plus 1 for M and N and Z. And now we look at A squared plus B squared. Well, that's going to be equal to 4M squared plus N squared plus M plus N plus 2. You can get that just from multiplying it all out. It's not too hard to check that. That's just like foiling out 2M plus 1 and 2M plus 1, both squared. But this is even. But then that tells us that A is related to B. So in other words, all odd numbers are related to all other odd numbers. And then finally, if A is in 2Z and B is in 2Z plus 1, in other words, A is even and B is odd, then A is not related to B. And I'll let you guys fill in the details for that. But essentially, you just do the same thing that we've done up here. A could be like this, and then B has to be of this form, right? But then that means that A squared plus B squared looks something like 4M squared plus 4N squared plus 4N plus 1. You only get a plus 1, right? But that's odd. But that's exactly what you need for this to not be related. Okay. So does that seem okay? So that means we've got two equivalence classes. Yeah. Okay, great. So let's see. let's look at maybe one from this section, 11.2. Which ones were assigned on 11.2? Do you guys have that in front of you? I was cheeky about it and I was like, oh, the ones that are 2 mod.
Oh, it was 2 mod 4.
4.
So it's like 2, 6, 10, 14, I believe.
Yeah, how about so 10. How about you guys look at 10? Think about it as sets. That's how you want to think about that. And then we'll look over 10. That's one that I think is an important problem, but is often found to be tricky. So yeah, I'll give you guys 10 minutes to work on 10 and then we'll look at some of the details. That's the sequence of events. All right, so let's look at this one. So it says that we've got two equivalence relations, R and S, on a set A, given R, S are subsets of A cross A. That makes them relations in the first place. And they are also equivalence relations. That means they satisfy those three additional properties, right? Reflexivity, symmetry, and transitivity. And then what we want to show is that R intersect S is also an equivalence relation. So let's look at it. So R and S are subsets of A cross A. That makes R intersect S automatically a subset of A cross A, right? You're intersecting two subsets of A cross A, that's going to be a new subset of A cross A. So all we really need to show is that it satisfies those three additional properties. So reflexivity, symmetry, and transitivity. So let's see how maybe we can start by doing that. So proof. So we'll do these one at a time. So first, reflexive. So maybe let's outline in a different color what we want to show, and then we'll do the necessary steps to get there. So we want to show that for all x in A, x is in R intersect S, right? So since we're looking at the intersection of two equivalence classes, and intersection is like kind of a notion involving sets, we probably want to use the set version of all of these properties like reflexivity, symmetry, and stuff like that. So it's important to know, like, or to be flexible with what setting you're working in and using the correct notation. So I think the set notation is the correct notation for doing this, like kind of as naturally as possible. Okay, so let's see if we can do that. So let's take an arbitrary x from our set A, and then let's notice that since R and S are equivalence relations, we know that x comma x is in R and x comma x is in S, right? Because we know that R and S are individually reflexive, right? Okay, but look, just by the definition of intersection, that means that x comma x is in R intersect S, right? So XX is in R intersect S, which is what we wanted, right? So let's see, let's make sure we did the right thing. So we started taking an arbitrary element from our set, right? And we showed that that arbitrary element was related to itself with this intersection equivalence relation. Okay. So let's see the next one. So that'll be symmetry. So let's see what we would need to do for that. If x, y is in R intersect S, then that means that yx is in R intersect S, right? That would be symmetry for R intersect S. Again, using the set notation for this equivalence relation, just because it's better suited for working with the intersections of sets and stuff like that. Okay, so that means we want to start on this left-hand side and then end up on this right-hand side. So let's suppose that x, y is in R intersect S. But now, by the definition of intersection, that means that x, y is in R and x, y is in S. And like I said, by the definition of intersection. But now we can use our hypothesis. Our hypothesis is that both R and S are equivalence relations. And equivalence relations are symmetric. So let's do that. So that tells us that yx is in R and yx is in S. So let's maybe point that out. That's because R and S are equivalence relations already. We can't use that over here. So we're going to have to, well, we're going to have to use it in all three of the states. Okay, but now we can mash that back together using the definition of intersection to give us that yx is in R intersect S. Again, that's by the definition of intersection. Now let's look at what we did. We started with xy is in R intersect S, and we ended with yx is in R intersect S, and that's what we need for symmetry, right? Okay. So let's look at transitivity. So let's blueprint what would need to be done for that. So we would need xy is in R intersect S and yz is in R intersect S to imply that xz is in R intersect S. That's what we need, right? That's the transitivity, but using the set notation and then applied to our R intersect S. So let's get going. We're going to essentially do the same kind of thing. So let's suppose that xy is in R intersect S and yz is in R intersect S. But then by the definition of intersection, we can rip these apart. That means that xy is in R and xy is in S and yz is in R and yz is in S, right? So just to be thorough here, this statement here split up into these two, and this statement here split up into these two. All right. Okay. Now we can mix and match these. So maybe we would match this one with this one and get the fact that xz is in R. So let's do that. So xz is in R. So that's because R is equivalence relation, right? Using those two green underline things. And then further, maybe using these two pink underline things, we'll get xz is in S. And xz is in S because S is an equivalence relation. That was one of our hypotheses, right? Okay, but now put that back together by the definition of intersection. We have that this means that xz is in R intersect S. But now looking at the very start of this, oh, I underlined it all in red and stuff, but maybe I'll overline in blue. Notice that we started here and we ended here, which is exactly what we needed to do to prove transitivity, right? So that means we've proven the three necessary properties for this to be an equivalence relation, making an equivalence relation. So that's the end of the proof. So like, there's no real tricks, right? It's just being very, very comfortable with the precise definition. Okay, so everything 2 mod 4, so I think that means 14. So let's do that one too. So I'll give you guys 7 minutes to work on 14. It has the same kind of flavor as this one. It's a little different kind of a result, but it has the same kind of flavor where you have to just be very comfortable with the precise definition and moving in and out of it. And we'll look at that after you guys play around with it for a little bit. All right, so let's look at this number 14. And it kind of answers the following question. So given any relation R, so underscore the fact that it's going to be a subset of A cross A, where A is a set, can we build it into an equivalence relation? So, for example, let's say we've got a 3-element set, which I'll just draw by dots. So let's say these are our 3 dots. And then our relation R is going to be like maybe this and that, right? So what could we do to take this relation R and build it until it is an equivalence relation, which we'll call S? So I'll put the same 3 dots here. And then I'll add these edges like that. And then this is not an equivalence relation at the moment, right? Because notice there's no loop on this point. So this point is not related to itself. There's no loop on this point. So this is not related to itself. And also there's an edge going from this point to this point, but not back, right? But that means that we don't have symmetry there. So that means we have to include some edges in here in order to build this into an equivalence relation. And which edges? Well, we've got to put a loop on this vertex, right? We need to put a loop on that vertex at minimum. And then since we've got an edge going from here to here, we also have to include an edge back. And now it is an equivalence relation. So I'll just write now it's good. So now it's an equivalence relation. And that was the shortest way of getting to an equivalence relation. We had to do those 3 things, right? We had to do this for reflexivity. We had to do this for reflexivity. And then we had to do this for symmetry. Notice we were able to leave these 2 edges disconnected though. That's fine. Okay, so now the question is there some algorithm to do this in general? And there is, and it's given by what's described in this problem. So let's look at this. So we have a finite set, so they make that point. I won't write that down though, right? And so we'll say, so define S by X is related to Y if and only if there exists X1, X2 up to Xn in A such that X is related to X1, X1 is related to X2, space this out a little bit differently. X1 is related to X2. Oh, sorry, this should be XSY, right? Because it's the S equivalence relation. I apologize for that. All the way up to Xn minus 1 is related to Xn. And finally, Xn is related to Y. So this like completes a path or something, right? So in the equivalence class R, we have this path X to X1 to X2 to X3 dot 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 all the way up to Xn to Y, right? So that's in the equivalence class S. Sorry, R. And then the equivalence class X says, well, we're going to make those equivalent to each other, the 2 on the outside, right? And that imposes transitivity. So that's what we did. We imposed transitivity. Oh, and I should say that like we're starting with R being reflexive and symmetric in our setup, right? So our setup already has a reflexive and a symmetric relation, right? So all we're building is the transitivity, and we're building this transitivity by every time there is some path, we are essentially adding in a new path that's a nonstop path, right? Okay, so now let's see if we can prove that S is an equivalence relation. So I'm not going to write all the details. So this is 14 from section something, 14, section 11.2. So you can read the setup in there, but you guys are playing around with it, so you know the setup. Okay. So let's check. S is reflexive, symmetric, and transitive. Right? Well, reflexive and symmetric, we don't actually have to do anything, or we don't have to do very much at all, because R is reflexive and symmetric. But let's check that just carefully. So let's suppose that X is in A, and then we'll point out that what we want to show is that X, S, X. So X is related to X via this equivalence, or this would-be equivalence relation S, right? Okay, well, let's notice. So let's set X equal to X, Y equal to X, and X1 equal to X in our setup, right? Okay, and then let's notice that with this setup, we have X is related to X1 because X1 is just equal to X. We have X1 is related to Y, right? Because again, they're both just X, and that is because everything is X and R is reflexive, right? So, we assumed R was reflexive. Okay, but these two things together tell us that X is S related to X by this thing right here, right? With N equals 1. So with a path length of 1. Okay, so now let's do the symmetric. So let's suppose that X is S related to Y. Okay, but what that means is that there exists X1 up to Xn in S such that X is related to X1, X1 is related to X2, all the way up to Xn minus 1 is related to Xn, and Xn is related to Y. Right? That's the definition of X being S related to Y, right? Yeah, by this over here, by the definition. But now we know that R is reflexive itself. So R is reflexive because R well, it was given to be reflexive, right? So that means we can just reorder this. So we can take this and write it over here as Y is related to Xn. We can take this and write it over here as Xn is related to Xn minus 1. And then all the way down to x2 is related to x1, and x1 is related to x. So we've just taken this list and reversed it. So we put the entries of the list in the opposite order, and we used reflexivity to like reverse the arrows essentially. But this means that y is s related to x. That's what we wanted. So we have symmetry. Okay. So let's look at transitivity. So let's say, let's suppose x is s related to y and y is s related. Related to z, yeah. And then what we want to show is that x is s related to z. Okay, but let's use the definition of this s relation. So that means that there exists, I'm going to use like, no, I think this is, yeah, maybe I'll use something different. So T1, T2 up to Tn, and U1, U2 up to UM, both in A, such that we have the following. So we've got a path of R relations from X to Y and a path of R relations from Y to Z. So we've got X is R related to T1, T1 is R related to T2, all the way up to Tn minus 1 is R related to Tn, and then finally Tn is R related to Y. So that would be, this right here is the equivalent statement of x, s, y. Okay, now let's do y, s, z. So that would be y, r, r, u1, u1, r, u2, all the way up to um minus 1, r, um, and then r, z. So we've got a path from y to z. And notice it might have a different length, right? That's important to notice that it might have a different length. So let's see, this means that y is s related to z. So those were our assumptions, right? So that's our hypothesis for transitivity along with the structure of S. Okay, but now notice we can just, it's the like computer science word for putting two lists together back to back, concatenate.
I don't know if it's not there.
Yeah, I think you just concatenate these two lists, right? So now, I mean, we could, if we wanted to, introduce some new notation to make it look exactly like the definition. So let's do that. So let's set x1 equal to t1, x2 equal to t2, all the way up to xn equal to tn, like that. And then we'll set xn plus 1 equal to y, because that's the next one. Xn plus 2 equal to u1. And then xn plus 3 equal to u2. So that would be the next one. All the way up to something is equal to um. Let's see, what is it going to be? It's going to be m plus n plus 1, right? xm plus n plus 4. But now notice with this new notation and just concatenating these lists together, we have x is related to x1, x1 is related to x2, x2 is related to x3, all the way up to, maybe we could call this even capital N if we wanted to. call this thing capital N just to make it look nicer. We have all the way up to x sub capital N minus 1 is related to x sub capital N, and then x sub capital N is related to z. Right? Where that just is from taking these two lists and mashing them together and then renaming it so that it looks like our definition of S over here. But again, by the definition of S, since we've got a list of things that are R related, starting at X and ending at Z, we have X is S related to Z. That's what we wanted. Okay. So that proves the transitivity, starting up here and ending down here. Now there's one more part to this problem, and that is that with this construction, we have actually created the smallest equivalence relation. So we don't have time to go through that whole proof, I don't think, but I do have time to sketch it. So also, this S is the smallest equivalence relation from this R, right? That's what it says. So how do you prove this? Well, what you want to do is suppose that we have another equivalence relation. So I don't know what you want to call it. T?
Yeah.
That's another equivalence relation. So let's suppose T is an equivalence relation such that R is contained in T, which is contained in S. Yeah. And then what we want to show is that, so the last step of this proof should be that T is equal to S. So what did we do? We tried to fit a new equivalence relation between R and S. And then we were like, oh, I can't do it. Can't fit one in between R and S. That means that S has to be the smallest possible one, right? Yeah. So I think you would just do this with like some sort of set inclusion. So you would do something like this. Let's suppose X and Y are in A such that X is T related to Y, right? And then use the fact that, or I don't know that you need to use the fact that R is a subset of T, but then what you're going to end up with at the end is that X is in fact S related to Y. So if X is T related to Y implies that it's S related to Y, that means that T has to be equal to S, given that T is a subset of S. So that's kind of the outline for that last part. Okay, so does that seem good? Yeah. Okay. So there'll be, just like proof class or algebra class, there'll be a short video to watch for Thursday.
Yeah.
And then the homework is that was supposed to be due tonight is going to be due on Thursday. Mm-hmm. And then there'll be stuff to do for Tuesday to prepare for Tuesday as well. And then the next bit of information we're going to spread over 3 days. So it's going to be functions, injective, surjective functions, the pigeonhole principle, and bijective functions. So that's the situation. So does that seem good? Everyone know what's going on?
Yeah. Yeah.
Solid.
So no one else will show up to the Zoom?
No. Someone's here. Thank you, Zoom attendee. You fill my heart with joy. I know that might have sounded sarcastic. I'm sorry with my tone of voice. I really wasn't sarcastic. I was like serious. Yeah. Oh, and also everyone in this class right now, including the Zoom person, thanks for doing your homework.
Oh.
You're in the minority.
What do you mean?
Yeah, I usually do the homework first and then do the overleaf like on that Tuesday.
Yeah, you know, yeah, that's the way to do it, right?
Yeah. Or leave on a different day.
Yeah.
And I'm trying to give you guys a start on a lot of the problems during our meetings, right?
Yeah.
I mean, that's the benefit of having lecture videos, is that we can like get a good start on all of the homework in class.
That was not so much to do on our own time.
Yeah, just to make it all, you know, kind of reasonable or whatever. So whatever.
Homework's by Friday.
That's good.
That's always the goal, but it doesn't end up being that way.
Yeah.
Okay.
It's been that way lately.
Have a good couple of days.
Yeah.
Yeah. Oh yeah, I may not see you guys.
In the morning.
Yeah, in the morning.
Oh yeah. I'll see you in the morning. Okay. Well, I'll wish you good luck then.